All right, can you guys see it all right? All right, wonderful. Sorry for that, guys. It's the first time I've shared the iPad through Zoom, so hopefully it sticks around well. All right, perfect. Hopefully the video. So I have it recording through the computer, so yeah, I think it'll be fine. Actually, what I'm going to do, I guess this is up to you guys. Are you guys fine with your names being in the video? I want to put chat up on the screen so it can record chat as well. But of course, you know that's a problem. If there's anyone that's uncomfortable with their names being present, just let me know and I will stop it completely. All right. So no one, and your name will only appear, of course, if you ask a question. All right. All right. So I'm seeing no one screaming out no. So I'm going to put this here. So this is also going to be in the video recording. All right, guys. So you guys don't see it, but I see it. All right. So welcome to the midterm review. Again, we're going to go over fall 2014. It's a good midterm. It's not too bad. And if you guys look at 2015, 2016, most of them are the same. Now, I have gotten a couple of questions concerning things from 2015 and 2016, and I will go over them. So if you guys do have questions from those midterms, feel free to ask them. This midterm review, we're going to go over 2014, but I want you guys to feel as comfortable as possible. So if you guys do have any questions, ask away. We're here for you guys, okay? I wanna make that clear. If you guys have any questions, to throw it in Zoom chat. Should be good to go. So what we're going to do is we're just going to get right on into it. So I'm going to scroll slowly. And 2014 again has almost identical format to what you guys will see in your midterm come Thursday. It's going to be 25 multiple choice questions, and the questions are going to be fairly similar to what we see here. The only difference is we actually have 5 options instead of 4. But that's going to be really the only difference. Oh, sorry, excuse me. Got the saliva stuck in my throat. Of course I do. All right. So I'm going to try and work together with you guys, because if you guys answer questions, that helps me know that you guys are understanding what kind of material is going on. So we're going to start off with question 1 together. It's going to be, again, a nice big group effort. We're going to have lots of fun. Question 1 says, let M be basically a 3x3 matrix, and then it gives us M. It has all those components, and it says then the first invariant of M, which is the trace, is equal to. So I say, okay, well, we know that the first invariance, the trace, they gave it to us, so the trace of M. And who remembers what the trace of M is equal to? Anyone remember? Sum of the diagonals, exactly. So this question tries to trick you by giving you a very complex matrix, but when we're talking about the trace, the only thing we actually need are those diagonal components, and it's going to be the sum of them. So I'd go 2 plus 7 minus 2. What do we get? Well, of course, we get 7. So if we look at A here, or I guess question number 1, it's going to be B. So is there any questions about that? Was that too crazy? As you can see, a lot of these questions are almost free marks, as you will. All right, so we're going to move on to the next one. It says let U equal 1, 10, and 3, while V is equal to 1, 0, 0. Then the orthogonal projection of U onto V is the vector, and it gives us 3 options. So all we need to do for projections is remember the formula. So I'm going to give you guys 2 different formats, and you guys tell me which one is correct. So let's say we have option A, which is the projection, so PROG, and we're going to have U onto V, and this is going to be equal to U dot V divided by the magnitude of V squared, and then multiplied by V. So this is option 1. Option 2 is the exact same thing, but instead of V, we have U at the bottom. So here, let's actually just copy this. Copy, paste. So then I'll just erase it. Let's see what you guys think. Actually, the dots are going to be the same. So U dot V, this will be U, this will be U. So question for you guys. Is this going to be option A or option B? What do you guys think? All right, I see an A in the chat. A. You guys are completely correct. It's A. The nice thing about this is once you guys have figured out which one it is, that's the only real trick to the question. When we ask you guys about projections, this is the only real trick that we're trying to test for. Do you guys do the right formula? So I'm going to erase all this down here because we know that that's actually incorrect. And then from there, we can just substitute everything. Now, the first thing is, if we look at the bottom here, we have the magnitude of v squared. V, as we can see over here, it's a unit vector. So what's the magnitude of v going to be? 1, exactly. We know that the norm of v is equal to 1 because it's a unit vector. So that whole bottom part there, we can actually just more or less ignore it. So we know that the projection is just going to be the dot product of u and v. So we're going to take all those components and multiply them together. So we're going to take 1 and 1, multiply them together. 1, 1. We're going to move on to the second one. So we have 10 and 0. So we have plus 0. And we move on to the third one, which is 3 and 0. So again, we're going to have 0 multiplied by v. So question for you guys now, what is 1 multiplied by v? Yeah, it's just v, exactly. So it's just going to be v. And if we look at the three different answers, we see that E1 here is actually just the same as v. So how is that one? That's a typical projection question. Once you guys know the formula to use, it's just plug and chug. The only trick lies in picking which formula. That's it. All right. So again, if I'm going too fast, if you guys have questions, just throw it in the chat. Other than that, we will continue on. So question 3, this is a fun one. It says, if lambda equals 0 is an eigenvalue. So this can be one of those eigenvalue questions. And xer, which so it could be any vector or any real numbered vector, is the associated eigenvector, then the following is always true except for one thing. So if we look down here, I'm going to just ask you guys right now, and don't just look at the solution. Which one do you think it is? Which one do you think it is? This is probably one of the harder questions on this midterm. All right, everyone's a little bit quiet. I understand. So first of all, let's just go through this. Whenever we see eigenvalues and eigenvectors, I want to go to the formula for eigenvectors. Remember, for eigenvectors, we say that m times p is equal to lambda p. This is kind of the formula we used to solve for eigenvectors. Does anyone believe that this formula that we've used many times is false? Who thinks that this formula is false and I just made it up and we've been doing the course wrong the whole time? No, this formula is always true no matter what happens. So we can look at answer B here, which is the same format, and we know that's for sure going to be true. Always. Now, if we were to look at this formula and say, okay, we have an eigenvalue that is equal to 0. Lambda equals 0. So what happens when I substitute 0 on this side? We got 0 times a vector p. And what happens when I multiply any vector by 0? What does it turn into? The 0 vector, exactly. So we know that this is going to turn into the 0 vector. So we know that this is also going to be true. So what students are going to start debating with is either A or C. I almost guarantee it. B and D you guys will figure out. It's going to be those two. Now, here's what's going to happen. Basically, what A is saying is that our matrix M, we know that it is going to be invertible. It's basically saying it's going to be invertible because the determinant does not equal 0. Option C is basically saying that we have an eigenvalue or eigenvector, which we had as x, is our 0 vector. So which one do you think it is? If we were to look at these two, or does not equal the 0 vector. Sorry, for part C. You guys say A. And someone said C. A, okay. So A is the correct answer. I'll give you guys that. But who knows why? This is where it gets really tricky. Who knows why? This is a very hard question. More like this. If we look at option C here, it's saying that our eigenvector cannot equal the 0 vector. That statement is always true. Always. No matter if we're talking about continuum mechanics, we're talking about linear algebra, whatever. An eigenvector by definition is always a non-zero vector. So we know that this is going to be true for sure. This right here, determinant does not equal 0. This, and I'll put it in pink so I can kind of give it some contrast, this is false. If you guys ever have an eigenvalue equal to 0, that means that your matrix is not invertible. Not invertible. Okay, guys? Hopefully that makes sense to you guys. This means that your matrix is not invertible. Because what happens is we still have the thing where we have m multiplied by this eigenvector x, which is not 0, and it equals 0. If we look at this formula right here that we just wrote, this is our formula for the kernel. If you guys remember, when we solved for kernels, this was the formula we used, and kernels are only associated with non-invertible matrices. Hopefully that makes sense to you guys. So what do you guys think? Is this question more clear now? Hopefully. I can see this one being a tricky one. All right, I'll take your lack of silence as good to go, Clayton. So we're going to move down. Now this is nice because this question here, question number 4, it's the exact same question that we had above. It's just making sure that you guys know the formulas. So I'm just going to write, we'll go back to red, and it says it wants the orthogonal projection of A on B. So we're going to say PROG projection of A onto B. So we know that the top of any projection formula is always going to be those two vectors dotted together. We're going to have A dot B, and then it's going to be divided by the norm of a vector squared, and then multiplied by that vector. So my question to you guys, are we using B as that norm squared, or are we using A as that norm squared? You guys are geniuses. Look at all the B's. Yeah, it's going to be B. So we're going to go right here and say, okay, this is our projection formula. It's important to note that this part right here is a scalar. So this will just give us a value. And then this B at the end, this is going to be a vector. So if we look at this, we can go through the options. Well, the first one, we have A dot B, which is good, multiplied by the vector B, it's good. But when we look at the norm at the bottom here, it's not squared. So we know that A is going to be incorrect. It doesn't have that squared sign that we need. If we look at option B, we know that it's just completely wrong because it uses A. We already said it's going to be B. You guys already laughed at me for such an easy question. And the same thing for C. So we know by process of elimination, it's going to be equal to D. But if we look at that, that's not the same form that we had. What we have to do is we have to realize that we said that the norm of a vector squared, and this could be any vector, it doesn't have to be B or A or whatever, it's always going to be equal to the dot product of that vector dotted with itself. So if I know that identity and I were to come back and substitute it up into here, well then we actually get the same format as answer number D. Does that make sense to you guys? I'm hoping that this wasn't too bad of a question for you guys. Hopefully not too bad. All right, again, stop me anytime. I'm just going to go through these nice and slow. Question number 5. It says, consider the following symmetric matrix. It says if the eigenvalues of S, lambda 1, lambda 2, and lambda 3, or sorry, if the eigenvalues are lambda 1, lambda 2, lambda 3, then the following has to be false. And it gives us basically 4 different statements concerning these basically eigenvalues. So whenever you see a question like this, and you see these 2 pieces of information, something should pop in your head. The first piece of information, symmetric. All right, symmetric. Whenever you see that, that's the first key. And the second key is whenever you're given eigenvalues. Whenever you see symmetric and eigenvalues together, what should you guys be thinking? What do you think? What should be the first thing that starts popping off into your head? Eigenvector? No, not quite. Diagonalization? That's on the right track. Because what happens when we diagonalize a vector? Or basically a matrix? We have 2 vectors in different coordinate systems, but they share very unique properties. What are those unique properties? So we have S, and we know that S prime is going to be a diagonal matrix, and it's going to be lambda 1, lambda 2, lambda 3. And we said that there are very specific things that these 2 matrices share together. Invariance. Exactly. Invariance. So determinants and trace, those are invariants. Exactly. So we know that the trace of S must equal to the trace of S prime because they're invariants. Now we say, okay, what is the trace of S? If I were to look at the trace of S, again, we're just summing those diagonal components. So it's going to be 2 plus 1 plus 1. So this is equal to 4. And this must be equal to the trace of S prime. So if I were to look at S prime and go down the list here, this is equal to lambda 1 plus lambda 2 plus lambda 3. Sorry, was there a question? No? So if we look here and we compare this over to A, it says lambda 1 plus lambda 2 plus lambda 3 is equal to 0. Is that true? Is lambda 1 plus lambda 2 plus 3 equal to 0? It's not. We said it's equal to 4. So we know right off the bat that this one here is false. But let's go through the other answers. The second one, part B, lambda 1 multiplied by lambda 2 multiplied by lambda 3. Do you guys know what this is? It doesn't exactly tell you guys it, but do you guys know what happens when we multiply 3 eigenvalues together? Like this, in this form. Determinants. You guys are geniuses. This is equal to the determinant of S prime. So what happens is part B, or I guess answer B, is saying the determinant is equal to 0. Well, we don't know it from S prime, but if we were to take the determinant of S here, and you guys can do this in MATLAB, Mathematica, whatever you guys want, you guys will find that this is actually equal to 0. So we know that B is correct. Answer C says lambda 1, lambda 2, and lambda 3 all must be real values. That's a property of symmetric matrices. If we have a symmetric matrix, symmetric, again the key word, the eigenvalues will always be real. Always be real. So we know that that's automatically true. And then D says that there's a coordinate system in which S has the form lambda 1, lambda 2, lambda 3. Well, we've already discussed that together, so yes, this is going to be for sure correct. Now we got a question. Is the product of the eigenvectors for symmetric matrices always the determinant? Yes, the eigenvalues, exactly. Because if we were to do our little fish method here, we would go lambda 1, and then we would multiply, if we were to go to the fish, we got lambda 1, or I guess, sorry, lambda 2. Lambda 2 times lambda 3 minus 0, and then minus this component, which is 0, and then plus this component, which is 0. It's just lambda 1 times lambda 2 times lambda 3. It's a little fun fact when you have a diagonal row like that. Great question. Great question. So that's kind of the hint here. Whenever you guys see three eigenvalues multiplied together, it's signaling that that's the determinant of S prime or M prime or whatever prime you guys want. So is there any questions about number 5? How are we feeling? Feeling good? Of course we're not feeling good. I'm keeping you guys at 5:30 at night. No one's feeling good. All right, let's go on to number 6. It says let I be basically a 5 by 5 identity matrix, and let P be basically a scalar that's greater than 0. And consider A, so I'm going to write this down. Oops, I'm not going to write it in highlighter though. A, which is equal to P times I. Then the following is false. So whenever you guys have a question like this, I recommend just writing what the matrix will be. So what's going to happen is we're just going to take I and we're going to multiply every value by P. Now I is the identity matrix, meaning that it's only going to have ones for diagonal components and everything else is going to be 0. So if we go P times 1, well, we're just going to get P. So it's going to be P 0, 0, 0, 0, 0, P 0, 0, 0, 0, 0, P 0, 0. This is the quality content you guys came for. 0, 0, P 0, 0, P. Because if I were to write it like this, the answer becomes very clear. Let's look at B really quick. A is a 5 by 5 matrix. Is that true? Is A a 5 by 5 matrix? All right, I hear a yes. Anyone else agree? Yes, exactly. It definitely is. We just wrote it. But if we look at C, it says that A is just a real number. Is A just a real number? Nah, exactly. It's not a real number. It's an imposter. Of course not. So we know that this is going to be false. The other ones are pretty easy to determine too. D says A is symmetric. If we were to look at it just by inspection, we can see that it is. And answer A, the determinant is equal to P to the power of 5. Well, it's one of those things that if you guys really don't believe yourself with answer C, you guys can throw it into Mathematica and verify, but you guys will see that that is also true. All right, so when it comes to those type of questions, I recommend just writing it out. Now, since you guys came here for the good stuff, I'll let you in on a little secret. This might be a very nice question to memorize for the midterm exam. Keep that in mind. All right, so we're going to move on to the next one. Question number 7. And this is another one that I almost guarantee will be in the midterm exam. It's been in 2014. I think it was in 2015, 2016. Again, such a common type of question. It says if Q1 and Q2 are rotation matrices and Q3 is a reflection matrix, which one of the following is false? So here's what I want you guys to do. If I ever give you guys a bunch of matrices and label them as rotation or reflection, the first thing I want you guys to do is state what the determinants are. So the determinant of Q1 is equal to the determinant of Q2 because they are both rotation matrices. And what is their determinants equal to? What are these determinants equal to? 1, exactly. And the reason why is because these are both orthogonal matrices. Now, the determinant of Q3 is a reflection matrix. So what is the determinant of Q3 going to be equal to? -1. So you guys are ready for that. -1. Now, in all of the scenarios listed below, it has all of the matrices multiplied together. So if I want to find the determinants of a bunch of matrices multiplied together, how do I do that? How do I do that? If I wanted to find the determinant of Q1 times, oops, I forgot to put 1. Q1, Q2, Q3, All I have to do is multiply by the determinants, exactly. So the determinants of Q1, well, we said that's 1. The determinants of Q2, we said is 1. And the determinants of Q3 is -1. So at the end of the day, we get the determinant is equal to -1. Now, before we start looking at the answers, if we have a determinant that is equal to -1, what does this mean our matrix is? What type of matrix do we have? Or what kind of coordinate transformation matrix do we have? Reflection, exactly. So we know that this is associated with reflection. So now we have all the information we need to go through the list. So it's wanting to know which one is false. The determinant's equal to -1. Well, we prove that to be true. The determinant is associated with reflection, or I guess the matrix Q. Well, we already said yes, that is also true. The matrix Q, which is Q1, Q2, Q3, is an invertible matrix. That is true. But I want to see if you guys remember why. Why do we know C is a true answer? What do you guys think? Exactly. A non-invertible matrix will have its determinant equal to 0. And since we have a non-zero value for our determinants, I'll highlight in pink, a non-zero value over here, we know that this is definitely invertible. And part D kind of shows this because it says the matrix is associated with rotation. Well, we said no, it's not. It's actually associated with reflection. So D, of course, is going to be the false answer. All right. So hopefully that wasn't too bad. We're going to scroll on down now to question 8. And it says, which of the following is an orthonormal basis set for R3? Now, whenever you guys see orthonormal, and I'll highlight it here, you guys want to be checking two things. What's the first thing that you guys should be checking? What do you think? Norm equal to 1. Exactly. You guys are on your game today. The norm of each of the basis vectors has to be equal to 1. Perfect. What is the second thing that we should be checking? Oh, you see, you guys were ready. The dot product has to be equal to 0. So any basis vector I dotted with a second basis vector j, it has to be equal to 0. I recommend, personally, starting with the norm is equal to 1, because that is something we can very quickly tell by inspection. So let's look at option A, which I just highlighted. If we were to look at E1, 1, 1, 0, does that norm equal 1? No, exactly. The only way that something can equal 1 is if only one of the entries is 1 and the rest are 0, or all of the entries are less than 1. Since we have two entries that are equal to 1, we know that the norm here is not going to be equal to 1. What about option B? So I'll erase this. I'll highlight option B. Is this an orthonormal basis set? Option B, an orthonormal basis set. No, exactly. The same reason as option A. We have another basis vector whose norm is not equal to 1. This would be greater than 1. So now we're going to get rid of that. So now we're left with just two options. Option C and option D. And if we look at them, 1 over square root 2, we can just tell by inspection that yes, these ones are going to have a norm equal to 1. So now we're going to have to go to our second thing, which is our dot product. All right, so we're going to flip on over to the dot product and say, okay, if I wanted to take E1 and dot it with E2, and this is for option C. Option C. What is E1 dotted with E2 equal to? Who knows? I know it's a little bit of calculations. It's not too bad, though. -1. So would this be an orthonormal basis set? No, because it does not equal 0. So we know right away that this is not going to be it. So it's going to be D. Now, do I recommend calculating things? Not really, because it's going to be obvious. If I have a positive number and multiply it by a negative number, it's going to be negative. And then if I add that to another positive number multiplied by a negative number, we're basically adding two negatives together. If we add two negatives, it's not going to ever be equal to 0. If we look over at option D, oops, kind of let my finger slip, we have a negative multiplied by a negative, so the first one's going to be positive, and then we're adding that to a negative multiplied by a positive, so this one's going to be negative. A positive plus a negative, that has a chance to be equal to 0. And if you guys do it, you will see that it definitely does. All right, so that's going to be question number 8. Again, orthonormal basis sets, you go to 2 checks. The norm and then the dot product must be equal to 0. After that, you guys are good to go. So we're going to move on now to question number 9. And it says, let x be basically a 4-component vector and y also a 4-component vector. And basically what it's saying is, what is x dot y? So let me just ask you guys, what do you guys think right now? What is x dot y? All right, I see an 8, 8, 8. Are you sure? Is dot product defined for 4 dimensions? Yes, see, there's no fooling you guys. It is indeed C, because if we were to multiply the components, we got 2 times 1 plus 2 times 1, etc. And this is going to be equal to 8. The reason why it's trying to fool you guys is because we have something very similar to dot product called cross product. Now, question for you guys, could we cross these two vectors? No. The cross product is only defined in R3 and R7. So if we had something in 4 dimensions, it wouldn't work. This question is just checking that kind of test. Can I make all exam questions like this? Well, they're going to be very similar, as you guys are going to see. There's not a lot I can do to really mix it up, so it's not going to be that much different. It's one of those things, too, that once you're in the exam, you guys are stressed out, it's 8 a.m., it's going to look harder than it actually is. So I apologize for that, but that's just kind of the reality of it. It's not too bad, though, as you guys are seeing. If you guys can get through this just fine, you guys will be honestly just fine for the exam. I'm not concerned. You guys are the smartest people I know. I'm not worried. All right. And if I'm not worried, you guys shouldn't be worried. Well, maybe most of the time. All right. So let's go on to question number 10. It says, let Q be an orthogonal matrix such that Q is equal to a bunch of components. It says, then the following the following are correct statements regarding the components of Q. So the key here is that we're given that Q is orthogonal. All right, Q is orthogonal. So what are the properties of an orthogonal matrix? What do you guys think? All right, exactly. So for the rows and columns, so not just the rows, but the rows and the columns, the dot product, so I'll just say A dot B or A dot C, whatever, they must be equal to 0. What's the other property that we have for these orthogonal matrices? So this is number 1. Oops. Determinant is equal to plus or minus 1. Now this right here is a fun one. So the determinant of Q is equal to plus or minus 1. Now this right here, this won't help you directly. But you guys have encountered this a lot on your assignment. You guys would input Q, and then you would say, Clayton, it's marking me wrong. And I said, well, that's because your determinant's not equal to plus or minus 1. So my question for you guys is, in order to make sure that our determinant is equal to plus or minus 1, what has to be true about the rows and the columns? We'll just say rows for now. What has to be true about the rows? Exactly. They must be normalized. So the norm has to be equal to 1. So again, property 2, the determinants of Q, it doesn't look like it helps you, but it actually does. It has to be normalized. So now we're just going to go through the statements. The first two, well, actually, who thinks it's A or B? Does anyone think it's A or B? No one? No one think? Okay, good. Because these are just garbage statements. These mean nothing to us. They're not exactly formulas. If we were to look at this statement right here for C and D, well, we can see that this is clearly dot product. And if we were to look at the formulas used in the second half over here, this one's clearly the norm. All right, so now we're going to go through. So let's look at part C. We basically have to do 2 checks. So I'm going to do the first check in pink, and then I'm going to do the second check in, I don't know, some other color. We have A1 times A3. So we got A1, and we're multiplying this by A3. Then we got B1 times B3. So B1 times B3, and then C1 times C3. And it's saying that that is equal to 0. Is that correct? Is that a correct statement? Yes. All right, so you guys are saying yes. So I'll give that bad boy a nice check right here. Now, the second statement says A1 squared, A2 squared, plus B2 squared, plus C1 squared is equal to 1. Is that a correct statement? Yeah, exactly. That's also a correct statement. Now, if we move on and we say, okay, well, everything is correct here, so I'm going to think that the answer is C. So let's put it as C, but let's also just check D. D, the first one for the dot product, it has A1 times B1, and then A2 times B2, and then A3 times B3, and it's equal to 1. Well, we know that that's 0 because it says it has to be equal to 0. So we know that this is false. But question for you guys. If this was equal to 0, would this be a correct statement? If it was equal to 0. Yes. So the one thing I really want to emphasize with you guys is it doesn't matter if it's rows or columns. It should be dotted to 0. In this case, it was it was a column. It wasn't a row. Now, the thing where this actually kind of really shows the flaws is if we were to look at that second statement, A1, B2, it's saying this. This vector composed of these diagonals is normalized. Is that true? Does the diagonal vector have to be normalized? No. It doesn't even make sense. When we look at orthogonal matrices, we're concerned with rows and columns, never diagonals. So we already know that this statement is going to be basically a bunch of garbage. So we know it's going to be equal to C. Any questions so far? Everybody's still very happy? All right, let's move on to the next one. So it says let U equal 1, 0, 1, V equals 0, 1, 1, and W equals -1, 0, 1. And it gives us a transformation matrix M. And it says then the ratio between the volume of the cuboid formed by the 3 vectors MU, MV, and MW, and that of the cuboid formed by this is, what do you guys think? All right, I'm back. My Lego block came in. I'm pretty excited. It's that Super Mario 64 question mark block. Oh, I'm going to have a good night tonight, guys. Yeah, sure. When I build it, I'll send a pic. Oh, I was excited. All right, back to the question. Enough about my daily life. So when we come to this question, this is a typical trap question. There's a lot of information. And honestly, there's 2 ways of doing it. If you guys know the trick, it's very quick. If you guys don't know the trick, it is absolutely disgusting. So whenever you guys hear, or not hear because it's a midterm, you guys are going to be reading, the volume of a cuboid. Do we have a formula for the volume of a cuboid? Is there a formula in our lecture slides somewhere that gives us the volume of a cuboid? Triple product, exactly. So triple product. If I wanted to find the volume of a cuboid by 3 vectors, we use triple product. So if I want to, I can find my initial volume as simply, what are the vectors? We go u dotted with v cross w. And then what I can do is I can find the triple product a second time for my vectors, for my transform vectors over here. So that's the mean way. In this question, though, we actually don't need triple product. I've talked about it before a little bit in linear algebra, but we also talked a lot about it when we talked about strain. If I want to measure how much something deforms before and after, what have we been using? Let's go back to strain. Let's think of something really simple. You guys have the displacement gradient or the deformation gradient. And we said that we can measure the volume before and after deformation by doing something to that deformation gradient. What did we do to it? Who remembers? Determinant. Exactly. If you guys ever want the ratio of volumes, oops, don't want the highlighter. If I want my deformed volume over my initial volume, so the ratio, all it's going to be is the determinant of whatever transformation we have. So in this case, we're transforming everything by m. It's just going to be the determinant of m. And if you guys were to look at m above here and you guys were to solve it, you guys will see that the determinant is actually equal to 1. So this question is one of the meanest. Because if you don't know that trick, that the determinant is the ratio of the volumes, then you are stuck calculating everything. And keep in mind, in 2014 here, these were in-person exams. Students didn't have Mathematica or anything like that, so they were stuck with their calculators trying to calculate all these different things. It was absolutely disgusting. So are you guys comfortable with this question now that you guys know the trick? You guys are just too kind. All right, good. As long as you guys are happy, I'm happy. Let's move on to the next one. So it says, let M be basically a 2 by 2 matrix. Let x and y be 2 component vectors, and let mx equal 1, 1, and my equal 1, 2. If z is equal to 2x plus 3y, then it's basically saying, what is mz? What is mz equal to? That's the whole point of this question. Are we given what m is? No. Is there any way to calculate m? That's the relationship for z. If I wanted that 2 by 2 matrix M, is there any way that we can actually calculate M? Yeah. You guys can try, but please don't. There is no way to calculate M. So is there enough information provided to calculate MZ? If I don't have M, how can I find MZ? With the relationship. Ooh, now we're getting juicy. What relationship do we have? That relationship with Z? Yes, but we have to apply it. So here's the secret to this question. And I almost guarantee this will be another great one for the midterm. The definition, all right, the definition of a linear map is this. And this is right from the slides. If I had a linear map M, and I were to substitute alpha times x, where alpha is a scalar and x is a vector, plus beta times y, this should be equal to alpha times m of x plus beta times m of y. This is the definition of a linear map. So we don't know m, but if we were to go through, do we know these components? We actually do. Alpha right here is 2. And then we're multiplying this by mx. Beta is going to be 3. So plus 3 times my. See, so this is where all the fun happens. So I'm going to erase this over here, because if we were to substitute everything over there, we have 2 multiplied by 1 plus 3 multiplied by 1 2. And if you guys were to just do the quick math, you guys will see that the answer is equal to A. Again, the reason why is this is a definition of a linear map. I know a lot of students may have forgotten about the definition and just plugged in x and y into here and were thinking, oh, this is good to go. But some students will see the m, and then that'll throw them completely off, and then they circle D. No. The definition of a linear map is if I were to substitute two vectors added together, it's the same as if I were to evaluate it separately and then add them together. Definition of a linear map. So how was question 12? Pretty good? Not too bad? Hopefully not too bad. Let's move on to question number 13. This is a fun one. It's one of the ones that if you know the trick, it's pretty simple. If you don't, well, it's also still pretty simple. So it says consider the vectors x, which is 0, 2, and 2, and y, which is 0, -5, -5. The geometric angle between these vectors is... Now my first question to you guys, a little bit off topic, but I want to test your guys' knowledge. Are these vectors linearly dependent or independent? Linearly dependent or independent? What do you guys think? Can I express x as a linear combination of y? Yes, I can. So if something is linearly dependent, they have the same kind of line of action. So if something has the same line of action, we know it's going to be one of two options. It's either going to be A, 0 degrees, or it's going to be C, 180 degrees. Now you guys are saying, Clayton, you're just talking garbage. How can I figure this out more simply? Well, what happens if we draw them? We know x is going 2, 2, so it's going to look something like this. And we know y is going -5, -5. So again, it's going to have the same slope. It's going to be a little bit bigger, but it's going to look something like this. So if I were to give you guys this picture right here, what is the angle between these two vectors? 180, exactly. So this is the simple way. If you guys were to just draw it, it's very clear that it's 180. But if you guys want to, we always can find the angle between two vectors using our dot product formula. So we could say, all right, cosine of theta is equal to x dotted with y divided by the norm of x. And I'm just going to do one absolute value sign. I'm not going to do two because it gets too boring. This, and then we can substitute everything in. So we say, all right, the norm of x is going to be √8. We can multiply that by the norm of y, which is going to be √50. And up top, we have the dot product, which is going to be -10 minus 10, so -20. And if you guys were to throw that in your calculator, this is actually equal to -1. So if I were to go inverse cosine of -1, I guess I need the little -1 there. You guys will see that this is also equal to 180 degrees. So it's up to you guys which one you want to choose. If you guys are scared, you guys can always just throw in the numbers into the formula. 5 and 8 for number 12. Yes, all I did was I just threw all this in here. So I'll erase it. Actually, I'll just come down here for it. So if I were to multiply the vector 1, 1 by 2, we have 2 and 2. And then if I were to multiply 3 into the vector 1, 2, I would have 3 and 6. And then all I have to do is add the components together. 2 plus 3 is 5. 6 plus 2 is 8. Does that make sense? I should have done that. I'm sorry. Okay, perfect. Yeah, as long as we're all good to go. And are you guys good to go with 13? Everybody happy? All right. I'm going to assume you guys are. Let's move on. So question number 14. Do you guys think that you guys will have a change of basis question in your exam? What do you guys think? Of course, exactly. Do you guys think that you'll have more than one change of basis question in your exam? Probably. I don't remember, but I remember there's for sure one. All right, for sure going to be one of them. So let's look at 14. 14 says the following figure sketches the process of an orthogonal change of basis from the orthogonal basis set B to the orthonormal basis set B prime. If the components in the basis set B are U, which is 1, 1, so this is going to be important, then the components of U prime and B prime are, so basically just figuring out the new components. So before we start talking about Q, because you guys know that this is going to start talking about Q, what is the formula to find U prime? Let's talk about the basics here. What is going to be the formula to find U prime? Exactly. U prime is going to be equal to Q times U. We are already given U, so the only thing that we need is Q. Now this is where things can start happening that you guys aren't going to like. Are we given a degree that we're rotating it by? Are we given an angle of any sort? No, we are not. So this is why you guys always have to remember, we can find it. Yes, that's true. I like the enthusiasm, but we don't have to. We can utilize the formula that Q ij is equal to E prime I dotted with EJ. If you guys are ever given, instead of angles, and you guys are given the actual new basis set, you guys always go to this formula. I'm going to say it again. If you guys, instead of given angles, are given these actual numbers, go to this formula. All right, that's going to be a big hint, especially for the exam, wink, wink. So if we were to look here and say, okay, we know that Q is going to have 4 components, and we're just going to go through. So the first component, Q11, I'm not sure where I'll draw this. I'll put it over here. It's going to be E1 prime dotted with E1. So we say, all right, well, we have 1 multiplied by 0.8 plus 0 times negative 0.6. So we're just going to end up with 0.8. 0.8. If we were to go E22 or Q22, E prime 2 dotted with E2, well, in this case, we are going to go 0 multiplied by 0.6. That's going to be 0 plus 1 multiplied by 0.8. So we know that this is going to be equal to 0.8. Now it comes to the off-diagonal components. So I'm going to erase these really quick. These are the simple ones. Actually, I'll even erase these too. So now let's say I wanted Q12, so E1 prime dotted with E2. Oh, and I'll erase it over here so we can go through it together. So E1 prime, 0.8 multiplied by E2, 0. And then we go to the second one, negative 0.6 times 1. Well, this is going to be equal to negative 0.6. And if you guys repeat the process, this is going to be 0.6 down here. So this is the hard part. Now we say, okay, I have Q. All I have to do is throw it into the thing above, so I can say U prime is equal to Q multiplied by 1, 1. And you guys have Mathematica during the exam, so you guys can throw this in really fast if you guys want. And you guys will find that it's actually equal to answer A. So how was that? Was that not too bad? I really want to make sure you guys know this, because there's a very, very good chance that I will make you guys do a change of basis, but I will not give you an angle. That's kind of the huge hint for the exam. All right, perfect. So again, if you guys are ever given numbers in the new basis set, then you guys know what to do. All right. And if you guys aren't given numbers, but you guys are given a picture, then you guys also know what to do. Because one of the things for these basis sets, remember, they always have to be orthogonal. So let's say I were to give you guys this right here. And I were to just tell you guys that this one right here is E2 prime, and this one right here is E1 prime. What is E1 prime going to be equal to, even though I didn't give you the vector? What do you guys think? What is E1 prime going to be equal to, even though I didn't give you its components? I just flipped it around. If it's going perfectly vertical, negative E2 as a direct message, yeah, 0, negative 1. Something like that. So you guys know what you're doing. You guys are perfectly fine. So I'm going to come down to the next question. It says the following figure sketches the process of rotation of any vector by 30 degrees. The rotation matrix Q that can apply such a rotation is... So this is one of those fun ones. So the first key piece of information is, what are we doing? We're rotating a vector. And if we look at our actual picture here, we're rotating it counterclockwise. So we're going to say counterclockwise rotation of a vector. Now, in our course, I have given you guys 2 rotation matrices, one for counterclockwise, one for clockwise. Which one would I use? Would I use the counterclockwise or would I use the clockwise for this scenario? See, you guys, one counterclockwise. The answer is clockwise. Those rotation matrices that were provided in the course, those are only for rotating the basis vectors. So if I were to rotate E1 and E2, then I would use counterclockwise. But I'm not rotating E1 or E2. I'm rotating U. So when I rotate a vector or a shape, it is the opposite rotation matrix of the basis vectors. So this is equal to a clockwise rotation of the basis vectors. Now, the first thing, if I were to ask you guys really quick for QCW, because that's what we want, the first component, is it going to be sine or cosine? This component right up top here. Cosine, exactly. So I know that this is going to be cosine, and this one's going to be cosine. So right away, if we were to look at our possible answers, we know it's not going to be B, and it's not going to be D. Now, the second part, we know that the other two, of course, are going to be sine. Now, my question is, which one of the signs are going to be negative, the top or the bottom one? For a clockwise rotation. Top, exactly. Now you guys may be saying, Clayton, how do I remember that? Honestly, write it down. You guys are given the counterclockwise and clockwise matrices. Just write them down and bring them into the exam. So if I were to look at this and say, okay, the sign that has to be at the top, or the negative sign, we know the answer is going to be C. So hopefully, again, not too bad. Any questions about this particular question, or are we still feeling pretty happy? All right, let's move on to some other questions. Question number 16. Consider R2. So basically a 2-component vector. Let x be a 2-component vector such that x is equal to 1, 2, and let E1 equal to 0, 1, E2 equal to 1, 1. Let B be a basis set for R2, And considering the basis set, x can be written as follows. Then the components alpha 1 and alpha 2 are, and if you see a question like this, all it is basically simple substitution. We're given that formula above. X is equal to alpha 1 E1 plus alpha 2 E2. So let's just sub everything we know. We're given x. It says that x is equal to 1, 2. And we know that this is equal to alpha 1 times E1. Now we're given E1 as 0, 1. And then it says plus alpha 2 times E2. And E2 we're given as 1, 1. So if we were to look here, it's actually a simple question because we have two equations and we have two unknowns. So if I were to write this out, I'll do it in different colors. We have 1 is equal to alpha 1 times 0 plus alpha 2 times 1. And then our second equation, which we'll do in blue, we have 2 is equal to alpha 1 times 1 plus alpha 2 times 1. So if we were to look at this, all we have to do is solve the equations. Which equation would you guys solve first, the pink or the blue? Pink, exactly, because it has a 0 in it. Alpha 1 times 0, well, we know that that is going to be nothing. So we got alpha 1 times 1 is equal to 1. Well, we can very quickly see, and I'll put it up here, that alpha 1 has to be equal to 1. If we go to our second equation, we have 2 alpha 1 times 1. Well, we know that alpha 1 is equal to 1, so I can just replace this right here with 1 plus alpha 2 times 1 is equal to 2. Well, we can see that alpha 2 also has to be equal to 1. So the answer is going to be B. These linear combination questions, they're of course going to be the easiest. All right? Because all you guys are doing is just substituting everything in and solving for unknowns. That's it. Now when you get to question 17, things get a little bit more tricky. It starts dealing with kernels. Now kernel questions students don't really like because kernels kind of suck. It says let M be a 3 by 3 matrix and X and Y are the kernel of M. Then the following is true. So before we do that, let me just ask you guys. If I were to take a linear map X and multiply it by a vector that is its kernel, what is it equal to? What does a kernel do? The 0 vector, exactly. The whole idea of the kernel is to find vectors that map to the 0 vector. So if I were to go M times a vector that's inside of its kernel, it has to be equal to the 0 vector. And it says that not only X is a part of the kernel, but Y is also a part of the kernel. So we know that M times Y also is equal to 0. So let's go through the options. Option A, mx is equal to my. What do you guys think? True? True, exactly. Let's skip B and go to C. M of x plus y is equal to 0. True? All right, I got one true. Anybody else? Any brave souls out there? True? All right, I'll take it. This is also true. Again, whenever you guys see a linear map multiplied by two things added to each other, always think back to the definition of a linear map. M of x plus y, in order for this to be a linear map, has to be equal to m of x plus m of y. Basically, we can split it apart. We know m of x is equal to 0. We know m of y is equal to 0. Therefore, mx plus my has to be equal to 0. So at this point, since we have two that are correct, we know it's going to be D, all of the above. And if we were to look at part B, we know it's going to be the same, because all I have to do to this equation that I wrote below is if I were to put 5 here, and then I were to put a 3 down in there, or I guess actually it's vice versa. And let me switch it. 5y, so 5, we have 3. It doesn't matter what scalars we multiply them by because we have the 0 vector. I can take 1,000,000 and multiply by the 0 vector. I'm still getting the 0 vector. So what do you guys think? Is the kernel question so bad? Yes. mx and m bracket x are the exact same thing. Yes, that's correct. We only write it in that way to show that they are two separate things, if that makes sense. Because sometimes we have scalars, so sometimes we would write it like m of alpha times x. That's kind of the more traditional format that we would have. But if I were to write it as m alpha x, well, then everything starts to get a little bit confusing. So that's why we try to avoid it. But yeah, great question. Great question. All right, so I'm seeing no questions about the kernels. Let's go on to question 18. It says we have a function from r to r, which is basically the absolute value of x. And it's basically asking, is it injective, surjective, bijective, whatever. So if you guys have one of these questions, please, 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 please just draw a diagram. Drawing a diagram is by far the easiest way of answering these questions. So we know the absolute value of x is going to look something like this. So all we're doing is we're doing the test that we did at the beginning of the course. The first test is it injective? How do I determine if it's injective? Do you guys remember? Horizontal line, all right? If I were to draw a horizontal line, which I did, is this injective? No. So this is not injective. And the reason why we draw a horizontal line is because we're checking if this intersects our shape or our function more than once. If we look, it intersects it once here, and it intersects it once over there. So since it intersects it more than once, it is not injective. So you guys are good to go on that part. So now the second question, is it surjective? What do you guys think? Is this going to be surjective? Oh, now we got the Civil War in the chat. All right, guys. Big brain time. When we look at surjectiveness, we always look at how our function's defined, and we look at the second letter r over here. In order for a function to be surjective, it must have an output for every value in there. So if we look right here, it wants the entire set of real numbers, meaning that it wants this entire set of real numbers. Question for you guys. Can I ever retrieve a negative number? So actually, let's switch to blue. Could I ever retrieve a negative value? Let's say this value right there. Yeah, no, I picked up on that for the next one. But could I ever retrieve a negative value? No, exactly. So we know that this is going to be not surjective. So if we were to look at our options here, f is surjective, we said nope. F is injective, we said nope. F is bijective. If something is not surjective and it's not injective, is it going to be bijective? Absolutely not. Exactly. If they are both injective and surjective, then it's bijective. But if not, or if it's none of them, then it has to be none of the above. All right. So moving on to the next part, it's the exact same question, but now we're changing that codomain. Instead of being the entire set of real numbers, we're now going from 0 to infinity. So before we get into the fun, I'm just going to ask you guys, is this function going to be injective? Injective. No. Because if I were to still draw a horizontal line, absolutely nothing has changed. I still intersect it twice. So we know that this is not injective. Oh, yep. Question for sure. Yep. It's basically, yeah, it is yes and no. So I wouldn't give you guys this format. This is a format that Sammer likes. I would just give you R to R. You wouldn't really have to worry too much about this over here. But yes, essentially it would mean the exact same thing. Yeah, great question. All right, so we said it's not injective. How could I have swapped or switched around 19 to make it injective? Could I have played with the question to make it injective? Yes, exactly. So if I look, I have two letters here. Let me just erase it and let me highlight them. I got this one right here in pink, and then I have this one over here in blue. The blue one, which was swapped, that always is associated with surjectiveness. It doesn't play any influence on injectiveness at all. If I were to play around with the pink one, then I could make it injective. This pink number, this is what I plotted over. So if I look right here in both questions 18 and 19, it wants me to plot over the entire set of real numbers. So I'll just keep it in blue, meaning I have to plot over this entire set of real numbers. But I think there was a question. Would it be injective if the domain was 0 to infinity? It would be. Because what happens then is I'm not plotting the entire thing. If this was R, let's say R plus union 0, then I'm only plotting this right here. And if I'm just plotting that portion right there, then my horizontal line test works. It only ever intersects once. Great question. But in this particular case, we kept R the same in both of them. In both cases, they go from R. So as we can see, entire set of real numbers. And in 19, we are still doing the entire set of real numbers. But I could change that to make it injective. So that is a great thing to notice. The only thing that I actually changed, though, was the codomain. Now, the codomain has to do with surjectiveness, and that is when we start looking at the y-axis, if you will. So before, we had to have a value for everything in the y-axis, but now we're only looking at this portion right here. And I guess I'll draw my function back. All right. So if I'm only considering that top portion of the y-axis, do I have basically, does my function return every value in that region for 19? Yes, exactly. So in this case, we would say that it is surjective. Surjective. So I come down here, we say, okay, F, I guess I'll switch back to red. F is surjective, but not injective. All right, so hopefully that makes sense to you guys. I think you guys will do just fine for that. And I modified the questions so that there's marks, the partial marks. So let's say, I'm just going to erase these right here in 18. Let's just say that it was bijective. And let's just say that these were my options. I'm going to erase this, but not. So this doesn't apply exactly to this question, but I want to let you guys know that I do have bonus marks. If something is bijective, is it also surjective? Yes. So in this case, even though C is the most correct answer, if you guys answered A, I would give you guys part marks. Same with B. I'd give you guys those part marks. I wanted to let you guys know about that to kind of make it even easier for you guys. All right. So we're going to move on to question number 20. Consider the vector x and y, which is x is 1, 1, 0, and y is 2, 0, 0. The area of the triangle formed by x and y is equal to something. Great question. If it's bijective, do you want us to select all three? You will not be able to. The way I have the quiz set up, you can only select one answer. So bijective would be the most correct, so you'd get full marks for bijective. If you guys pick surjective, then I'd give you guys 50% of the marks, something like that. Yeah. All right, so on to 20. How do we find the area between two vectors? What do you guys think? Area between two vectors. cross product. Now, you guys have to be careful with this. Cross product is absolutely correct. But does the cross product return you with the area between two vectors? Or does it return you with the area of something else? The parallelogram. Exactly. So if I were to cross these two vectors and then take the magnitude, I'm actually getting this area like this. But what's nice is this. If I were to know the area of that parallelogram, could I find the area of the triangle? What do you guys think? Can I find the area of the triangle if I know the parallelogram? Yes. All we have to do is divide by 2. So in these type of questions, we need to find the area of this parallelogram, and then we just divide by 2. So we said that, and I'll go to pink, we want to cross them together. So C is going to be equal to A cross B. And you guys can do the cross product however you guys want. So we'll go back to Engine 130 where we have that I, J, K, and we have 1, 1, 0, and then 2, 0, 0. You guys can do whatever method you guys find preferable. Me personally, I like doing that fish method. So this is going to be equal to, in the, actually let's switch to blue. I'm looking at the I component, so I'm going to make my fish. 1 times 0 is 0, minus 0 times 0, well that's also going to be 0. So my first component is going to be 0. Then I erase these two. I go to the next one. I have the J component, make a fish. 1 times 0, 0, 0 times 2, 0. So this one's also going to be 0. Nice and simple. And then I go to my last component, which is going to be K. I make another fish. 1 times 0, 0, minus 1 times 2. Oh, so we get minus 2. And this leads me to my next question, which was already asked, which is great. Is that the area? This was a direct message, so you guys don't know what was being asked. But is that the area? No, that's a vector. So how do we find the area from this vector? Magnitude, exactly. So once you find that, you want to find the magnitude of this vector. So this is going to be equal to the square root of 0 squared plus 0 squared plus 2 squared. It's technically negative 2 squared, but you guys know it's all the same. So we get this is equal to 2. Now this is why it's important to know that it's a parallelogram. This 2 here is the area of the parallelogram. So a lot of students would pick 2, they'd be happy, and then they get mad later on when they realize that they're wrong. The area of the triangle, so I'll go area of the triangle, is equal to the area of the parallelogram divided by 2. So of course 2 divided by 2, it's going to be equal to 1. So I'm going to erase that, go back to red. We know that this of course has to be equal to 1. Does that sound good? You guys have to be careful because I've seen it where they ask for the area of the triangle, but then I've also seen it where they ask for the area of the parallelogram. So it switches. You never quite know what they're going to ask. If they ask for the triangle, make sure you guys divide by 2 at the end. All right? Perfect. Let's move on to the next question. Let M be a two-dimensional matrix, or a 2 by 2 matrix. And it gives us what it is. And it says the kernel of M is equal to, and it gives us a bunch of different options. What equation do we have to use to solve for the kernel of something? Exactly. M times P is equal to 0. I typically use P for eigenvectors and I use V for kernel. So what I do is I say MV is equal to 0. So if I were to write this out, I have 1, negative 1, negative 1, and 1 times V1 and V2. Again, this is what I'm trying to solve for. And I want to make this equal to 0. So if I were to look at my first equation, I get V1 minus V2 is equal to 0. What can I conclude from here? What does V1 have to be equal to? V2. Exactly. V1 is equal to V2. So I will get my kernel as long as the two components in the vector are the exact same. Let's look at what A has to offer. It has a vector 0, x2 where x2 can be anything. Will those two components always be the exact same in option A? No. One of them 0 and the other one could be anything. I could have 0 and 69. They're not going to be the exact same. So this is a big fat no. The kernel of M is equal to the 0 vector. Those two components are going to be the same. What do you think? Is B the right answer? No. The kernel of M is only equal to the trivial solution for invertible matrices. This matrix is not invertible. If you guys want to check the determinant of M, if we were to calculate it, 1 times 1 is 1, minus 1 times 1 is 1, so this is going to be equal to 0. This is the trivial solution. It's the number one trap. You guys got to be careful for that. Let's look at option C. Vector x, which is x1, 0, where x1 can be anything. Are those two components always going to be the exact same? No, exactly. But how about option D? A vector x1, x1, where x1 can be anything. In this case, will those two components always be the exact same? Yes, exactly, because they're both x1. How can they be different when they're the exact same? And yes, I don't want to do this. Can I explain B again? Of course. So B, this right here, is the trivial solution. This only applies when the determinant does not equal 0. Only applies when the determinant does not equal 0. If we look at this matrix, our determinant is equal to 0. Therefore, this right here, it's trivial. This will never actually exist. Does that make sense? I'm hoping it does. Gotcha? Okay, perfect. All right, we're nearing the end, guys. So you guys got this. You guys haven't had any actual tough questions. So you guys obviously know what you're doing. So let's look at this one right here. This one's fun. This has to do basically with these statements right here, the arrows. Basically, what I can say is one statement applies another and vice versa, or not. So let's just go through them one by one. The determinant of M is equal to 0 implies that M is not invertible. Is that true? Option A. If my determinant is equal to 0, my matrix is not invertible. Is that true? Yeah, exactly. But what happens if I go backwards? If I were to say M is not invertible, can you guys already know that the determinant has to be equal to 0? Yes, exactly. So this one's good to go because that works both ways. It doesn't matter which way you go. My determinant is not equal to 0, therefore it's invertible. Well, that's true. What happens if we go backwards? M is invertible, therefore the determinant does not equal 0. How about that statement? Is that good to go? Both ways? Option B. Is it good to go both ways? Yes, exactly. Now this is where it starts getting fun. My determinant of M is less than 0. M is invertible. Is that true? Just looking at the forward way. Determinant of M is less than 0. My matrix is invertible. Yes, exactly. But what happens if we go the opposite way? I were to say my matrix is invertible. Is the determinant going to be less than 0? Always. No. So this right here is false. Going forward, it's definitely true. But going backwards, it's not true because my determinant could be greater than 0 and it's still invertible. So that one does not imply the other one. If we were to look over at part D, it kind of has how it should be written. If my determinant is greater than 0, it's invertible. True. But M is invertible does not exactly go backwards. So yeah, it'd be C. All right, perfect. Question 23. let M be a 3 by 3 matrix, where M is equal to P times I, and I is the identity matrix, and P is just some random scalar. Then the following is an eigenvector of M. Now, I'll be honest with you guys. Well, actually, let me ask you guys. In Dr. Sammer's midterms, did he have questions that repeated through multiple years? Same question, different midterm. Yes, he did. Could you guys imagine if I did that? That'd be just crazy, especially on a question like this. All right, so in these type of questions, I always recommend drawing it out. So M is equal to P times I. So M is equal to P times I. So we know it's going to just be P 0, 0, 0, P 0, 0, 0, P. And it says, which of the following is an eigenvector of M? Yeah, poo, haha. You guys all laughed at the lecture. I look like an idiot on YouTube teaching second graders. The maturity. No, it's funny because someone in the Discord's poo cow. I can never get over that. You guys should see the first year Discord names. Half of them had to get changed because they were so offensive. Oh, they're great. It's one of those things that you can't really regulate Discord. I don't know why the university decided it. I love it personally, but it's just asking for a lawsuit. Keep it clean in 398. Save it for Yong's Discord, okay, guys? Keep it away from mine. All right, back to the actual quiz. We have our matrix here. It wants us to find the eigenvectors. First question, is M symmetric? Is M symmetric? Yes. So if M is symmetric, is there a coordinate system M prime such that there is lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0? Yes, exactly. And we said that to go from one coordinate system to the other, M prime is equal to Q times M times Q transpose. Now, if we look here, I take a matrix that's already diagonalized, and I want to transform it to another diagonalized matrix. What is the only actual option I have for Q where I get the same thing when I multiply it? Identity matrix. Exactly. So Q has to be equal to I, which is just going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is the trick, because what are the rows of Q? What are my rows of Q? Eigenvectors. So these right here, ladies and gentlemen, are my eigenvectors. So let's go down the list. I'll go back to red. X 1, 0, 0. Is that going to be an eigenvector? Option A. Is that going to be an eigenvector? Yes. So check. Option B. X is 0, 0, 10. Is that going to be an eigenvector? Yes, exactly. Option C. 0, 10, 0. Is that going to be an eigenvector? Yes. These are all perfectly valid eigenvectors. The only trick that some students might have, oops, let me just go back to normal, is they will get lost with the 10. Remember that eigenvectors just indicate a direction. They don't have to be normalized. So my vector, if I were to go here, 0, 1, 0, does this have the exact same direction as 0, 10, 0? Same direction, right? So therefore, it's still actually an eigenvector. The only time when you guys have to worry about normalizing the eigenvectors is when we're dealing with our orthogonal matrices. Otherwise, the eigenvectors actually do not have to be normalized. So that's the trick to this question. Again, don't forget it. It'd be a really nice examination question. All right? All right. So I'm going to erase this, and we're going to go into our final question of the night for this exam, and then I'm going to cover one other question that you guys will see. Q will always have to be orthonormal, right? Q will actually always have to be orthogonal. Yes. It'll always have to be orthogonal for our transformation matrices. Great question. All right, so we're going to go into the last question. Which of the following is a subspace of R2? I'll be honest, guys. You guys have been so nice. I'll be nice. I'll give you guys a big hint. I will have this exact same question. Well, not exactly the same, but I will have the beginning the same. I will give you guys a question that says, which is this a valid subspace? There will be one subspace question on your exam. Telling you guys now. Full transparency. Question is, how do we determine if things are a subspace? There's two checks. What's the first check? Who remembers? Closed under addition. So I'm just going to put addition. Exactly. What's the second check? Multiplication by a scalar. Exactly. Multiplication by a scalar. So in order to basically check, all we have to do is try and find cases that disprove our subspaces. If we look here, these are basically the format that we have. And when we're trying to disprove them, we always want to look at the restrictions. So as we can see, a lot of these have restrictions. And usually the actual subspace is the one with the least restrictions. If I were to look at these right here, all four of these, which one of these options, A, B, C, or D, has the least restrictions? C. It said that x1 and x2 can be absolutely anything. This is actually going to be our answer. But the question is what happens if it wasn't clear? How can we check if these do not abide? What we have to do is we have to take two vectors that are in the subspace and then add them or multiply them by a scalar and see if they remain in the subspace. For example, let's look at subspace A right here. It says the vector is going to be x1 and 0, where x can be between 1 and 5. So if I wanted to, could I have 3 and 0? Is this in my subspace? Yes, it is. And let's say I have a second vector, 4 and 0. Is this vector also in my subspace? Yes, it abides by all the restrictions. Now, what it means by addition, it means that I can take two vectors in my subspace, and when I add them together, the resultant also has to be in the subspace. So let's say I add these two together, and I get 7, 0. Is that vector in my subspace? No, because that x1 component is now greater than 5. So therefore, this one violates addition. I could do the same thing for multiplication by a scalar. I can have the vector 3, 0, and you guys all agreed that this was in my subspace. But let's say I multiplied it by -1, and I now get -3, 0. Is -3, 0 in my subspace? No, it's not, because it's not between 1 and 5. So this violates addition and the multiplication. So if you guys ever want to disprove something, just try and find a way to show that the restrictions aren't being met. For instance, we can go to, actually, let's not do this one. Let's go over to B, x1 and x2. So for instance, I can take 5 and 5, both in my subspace. I can add this to 4 and 4, which is also in my subspace. But then I get 9 and 9, which is not in my subspace. So what do you guys think? Proving subspaces, is it too bad? The only two things I will ever ask you to check is addition and multiplication. I would not try and get you guys on one of those other axioms, so you don't have to worry about that. Oh, that would be mean. All right, what do you guys think? That was the 2014 midterm. Any general questions? I'm going to solve one other type of question for you guys down below here because I've been asked about it quite a bit. But just referring to the 2014 midterm, is there any particular type of question? So if I ever give you, here's the trick. So when it comes to Mathematica, if I were to give you guys a question and I give you guys all the values, you guys can easily throw it into Mathematica. I'm not going to try and give you a calculation-heavy Mathematica question because that's just wasting your guys' time. What I've done is a lot of the matrices that I give you guys will have unknown components. So you guys won't be able to directly use Mathematica some of the time, if that makes sense. Yeah, no problem at all. All right, so I'm going to answer one more question because I've gotten this quite a bit. How many of you guys have seen one of these questions? We have Rn to Rm, or we have Mn to Rm. Do you guys like those questions? And they ask you for the number of independent constants. Do you guys want to know how to solve these, or you guys already know how to do them? You guys are just quiet. Don't really care. Send help, please. All right, but first of all, I got a direct message. Are we allowed to access old midterms and solutions during the exam? Absolutely. You guys can have as many midterms, any study material you guys want. Completely open book. For the first one, you're right. The number of independent constants for the first one is simply just going to be n times m. That's it. So if we had, let's say, R6 to, I don't know, R4, all we're doing is taking 6, multiplying it by 4. It's going to be equal to 24. Sound good? For the second one, the 24 represents basically the tensor that I would take to get from one to the other. And I'm going to try and explain it more after I show the second one. Because they're both related to each other, but it's one of those things, I'm not going to lie, it's not very easy to visualize. One of the problems with this course is that we do deal with tensors. We're not dealing with matrices. So these operations aren't actually matrix operations half the time. They're tensor operations. For the second one, it's going to be n squared times m. All right, n squared times m. Basically, the number of components in the matrix multiplied by the components of the vector afterwards. So let me come down here and let me try and show you guys what exactly is going on. Let's go 2 by 2. So if we were to look at a matrix, let's say we have A1, A2, B1, B2. So this would be M2. And I want to transform it into, let's say, R3. So this would be, I don't know, we'll go C1, C2, C3. So if I were to use my formula really quick, 2 squared is 4, multiplied by 3 is equal to 12. So 12 would be the answer. But what is this 12? Well, if I were to look at one of the values in here, C1, and I were to calculate it based on the matrix, we know that C1 is going to be a function of something times A1, something times A2, something times B1, something times B2. C1 is going to be a function of those four components. Do you guys agree with that? Hopefully. If I wanted to calculate them, it has to be a function. And then the same thing happens for C2. It has to be a function of something times A1, something times A2, something times B1, something times B2, and the same thing. So this one would be a function of A1, A2, B1, B2. And if I were to count all of these, there's 12 components. And then it gets kind of infinitely higher. Now, do I want you guys to know what this means or how to do it? No. All you guys will have to do is just that. All right, so that there's a nice easy 4% of your marks. If you guys get to the exam question, just look at this formula. That's it. Nice and simple. All it basically is, if you look at these formulas, is taking the number of components that we originally start with and multiplying them by the number of components that we have in the end. 4 components times the 3 components that we end up with, we get 12. And you guys can do that for any sort of scenario. What would the question be? It would be something like, let f be a function from, let's say, m6 to r3. What are the number of independent constants? The number constants describing this motion. And then I'll give you 1, 2, whatever. So in this case, 6 squared times 3. So it's equal to 36 times 3. What's that going to be? 108? I don't even have an idea. 108? I just throw it in MATLAB. Throw it in Mathematica, whatever you want. But you guys see, that's all you guys need to do. It's just basically look at these two numbers. That's it. I'm hoping that takes a lot of stress off of you guys for the exam, because I know a lot of you guys were asking about that specific question. Nice and simple. All right, I got a thumbs up. That makes me happy. All right, so with that being said, I've talked about what I want to cover. Any questions from you guys? No problem at all. I'm happy to help. I hope I took some stress off of you guys. I can see that you guys look mildly defeated today in today's lecture. So hopefully that changes and you guys are able to get some more rest and relaxation. Yes. Okay. Yeah. You definitely could do that. Yep. If you can visualize it, you can definitely do that, but it's kind of hard to visualize sometimes. So if you can do that, that's great, but I would never expect a student to be able to do that. Yeah, no problem. Yeah, no problem at all, guys. I'm happy. Hopefully you guys are doing good. Again, I have this recorded, and I will be posting it to YouTube right after this. Okay. Yep. Oh, we don't have to assume it's specifically one matrix or another. The determinants of a matrix is always measuring the change between the vectors. When it comes to the determinants of the deformation gradient, those vectors are strain vectors, so we can figure that out. But in general, the determinant is always a measure of basically the change after the transformation. Yeah, no problem. I had a private message. Did I do any new content today? Yeah, so today's lecture, which will be up right after this too, I'm uploading both the review and the lecture today at the same time. We talked about stress. We talked about the Cauchy stress tensor. So it's new content. I just reminded everyone that there is a midterm on Thursday, but that's it. We didn't do any sort of review. Yeah, no problem at all. All right, guys. Well, I'll stick around for a little bit. You guys are free to go, of course. If you have any questions, just let me know. You guys will do great. Don't worry about the exam. You guys will do absolutely fantastic. I believe in every one of you. Civi 398. I love Civi 398. I probably could, but yeah, I don't know. The dean would get mad. I've been getting in trouble for snooping in other classes. No problem. You have a great night.